In this video, we discuss the learning outcome number 5 from lesson 4.2, which is all about the multiplication rule. We're also going to determine whether two events are independent. We'll learn about independent and dependent events. And we're going to describe how the sampling method affects the independence of events. So here is some notation for probabilities of compound events. So this means, or is read, the probability that A occurs and B occurs. So this is the probability that A and B both occur. And this notation is the probability that B occurs given that A has already occurred. So we're assuming that A has happened, and then we're saying, okay, well, given that A has happened, what is the probability that B would occur in that context? So one way that we can visualize these is with some Venn diagrams. Here we've got the probability of A and B. So this is the probability that A occurs and B occurs. In order to find the probability that A occurs and B occurs, we need to, well, we'll see. We're going to use the multiplication rule. And this probability of B given A can be thought of this way. We're going to think of all of the ways that A can occur. And then we're going to say, well, given that A has occurred, what is the probability that B occurs? So we're looking at the number of ways that B occurs when A occurs, and we're dividing by the total number of ways that A occurs. And that's going to give us the probability of B happening given that A has already happened. So all of this is related to the multiplication rule. And again, the multiplication rule allows us to find the probability that A happens and B happens. There are a couple of ways that we're going to look at this. We're going to look at the intuitive approach and the algebraic or formulaic approach, the multiplication rule. In the intuitive approach, this is what we'll say. We'll say to find the probability that A occurs, and then after that, the event B occurs, we're going to do the following. We're going to multiply the probability of event A by the probability of event B, But we're going to modify that probability of event B, ensuring that we have assumed that A has already occurred. Now, again, that's exactly the same thing as taking the probability of A and multiplying by the probability that B occurs given that A has occurred. So this is a symbolic way to say exactly what we just said in that intuitive approach. We're going to multiply the probability of A, that's P of A, by the probability that B occurs given that A has occurred. That's what this says here. And so we have this formula. Now, in practice, I think of this formula, but when I think of this formula, I'm really thinking about the intuitive approach. I'm thinking about what this means and what this means, and then I'm finding those ratios and I'm multiplying them together. And that's giving me the probability that A occurs and B occurs. And again, the probability that B occurs given that A occurs can be found this way. You want to count the number of ways that B can occur given that A has already occurred. And then you want to divide by the total number of ways that event A can occur. So it's like this Venn diagram over here on the right. You find the number of ways that A can occur. That's all of the simple events that are in this blue circle. And then you say, okay, well, how many events and how many of those events could B occur? So we take the number of ways that B can occur given that A occurs, which is given by that intersection in the Venn diagram, and we divide by the number of ways that A can occur. So that's what that symbol means. But in practice, I'm not thinking of that. I'm thinking, let's take the probability of A and then multiply it by the probability of B occurring given that A has occurred. So let's do an example. So this says, use the data in the following table, which lists drive-through order accuracy at 4 fast food chains. Assume that the orders are randomly selected, from those in the table. So we've got our table right here. You've got 4 restaurants, restaurant A, restaurant B, restaurant C, and restaurant D. And you've got all the accurate orders from all 4 restaurants listed here. And all of the inaccurate orders in our sample are listed in the second row. So the question says, if 2 orders are selected, Find the probability that they are both accurate orders. Assume that the selections are made with replacement, and then assume that the selections are made without replacement. So basically, they're asking us to find the probability that both orders are accurate twice. We're just thinking of selecting a little bit differently. So first we will assume that the selections are made with replacement, and then we'll assume that selections are made without replacement, and then we'll see how that affects the probability. Okay, first we need to find the total number of accurate and inaccurate orders in the sample and use those to find the sample size as well. So we're going to create a table like this. I am going to fill in this column on the right, and I'll do that on my paper. I'll share my screen with you. Let's see. Okay, so here's my paper. Now, because we were asked about accurate orders, I need the total number of accurate orders, and I also need the total number of orders that we have in our sample. So in order to do that, I'm going to total up the number of accurate orders that we have in our sample by adding these entries right here, and I'll total up the number of inaccurate orders we have in our sample by adding these entries right here. So we've got 329 accurate orders from restaurant A, 264 from restaurant B, 249 from restaurant C, and 145 from restaurant D. So there are 987 accurate orders in our sample. And then we'll add these guys up, 33 plus 54 plus 31 plus 13. Those are the inaccurate orders from restaurants A, B, C, and D. So we have 131 of those. So if we want the total number of orders in our sample, we just add these two numbers together. We add the inaccurate orders to the accurate orders, and we get 1,118. Now, if we wanted to, we could also total up the number of orders we have from restaurant A, the number of orders from restaurant B, the number of orders from restaurant C, and the number of orders from restaurant D. But that's actually not really important right now, because this question is asking about the probability that both orders are accurate. So what I really need is the sample size, which is the number of orders that we have, or this 1,118. And I also need to know how many orders are accurate and how many orders are inaccurate. So those two numbers are listed right there. And let's go back to the PowerPoint. Okay, so we're over here. We want to find the total number of accurate and inaccurate orders, and we did, and then we add those up to find the sample size. So it's the total number of orders in our sample. So we're over here. So I got 987 for accurate orders, 131 for inaccurate orders. That's good. It's consistent with what I have on my paper. That means I didn't type it in correctly into my calculator. And then I've got 1,118 total orders. Okay, so now I'm trying to find the probability that both orders are accurate. Since I want the probability that the first order is accurate and the second order is accurate, the fact that that's an and statement, the fact that I'm talking about both orders having some property, or one order having this property and another order having this property, that tells me I have to use my multiplication rule. So I'm going to take the probability that the first order is accurate, and then I'm going to multiply by the probability that the second order is accurate, given that the first order is accurate. So you want to keep that in mind. Okay, so all we need to do in order to find this probability is find the first probability and then the second probability, and then we'll multiply them together. So the next thing we need to do is just find the probability that the first order is accurate. That's actually pretty simple. You're just going to take the number of accurate orders that we have in our sample, which is this 987, and then you divide by the total number of orders in the sample, which is 1,118. So you do that, and you divide, and you're going to get some number between 0 and 1. That's the probability that that first order is accurate. Now, let's make that first assumption. We're going to assume that selections are made with replacement. So that means you can imagine putting all 1,118 orders in a hat. You've got a hat and it's got 1,118 pieces of paper and each one represents an order. You pulled one out of the hat and you say, what's the probability of getting an accurate order? It was 987 over 1,118. You did that. When they say assume selections are made with replacement, what they're saying is you want to put that order back in before you find the probability that the second order is accurate. So if there were 1,118 orders with 987 that were accurate, and you pulled one out, then you want to do the following. You want to find the probability that the second order is accurate, given that the first order is accurate. Well, since the first order, well, whether or not the first order was accurate, there are exactly the same number of accurate orders in our sample now, and there are exactly the same number of total orders in our sample now, because we made the selection with replacement. We put that order back in to the hat, basically. And so we're just going to take the number of accurate orders and divide by the total number of orders. So we get exactly the same proportion as before, that 987, excuse me, out of 1,118. So note that this is exactly the same probability that we found for the first accurate order. It's because we're saying, what's the probability that both are accurate? The probability that the first one is accurate is the number of accurate orders out of the total number of orders. The probability that the second one is accurate is exactly the same because we put the first order that we found back in, put it back into the mix. And now we've got 987 accurate orders over 1,118 orders again. So this is happening, we get these same numbers because we're making the selection of that second accurate order, or we're trying to find that second accurate order, the probability of that, we're making that selection with replacement. So yes, it's the fact that we're doing it with replacement that the number of orders in our like sort of hat full of orders, if you will, is exactly the same. Okay. Now we want to multiply those probabilities together to find the probability of two accurate orders given that the selections are made with replacement. So you just multiply. You get 987 over 1,118 times itself, which is approximately this. And I have rounded to 6 decimal places because the other version where selections are made without replacement is actually very close to this. And I wanted you to be able to see the difference between the probability due to two orders being accurate when the selections are made without replacement and how that compares to the probability when selections are made with replacement. So that's why I've got so many digits here. Okay, so that was our first one. Now we're going to do it again. This time we're going to make selections without replacement. So you still use the same formula and the probability that the first order is accurate stays exactly the same. We just have to think about that probability that the second order is accurate now. And we're assuming that the first order was accurate. And we're assuming that selections are made without replacement. So you've got this hat and it has 1,118 orders in it. And 987 of those were accurate. And you already took one out and it was accurate. The question is, what is the probability that the second order is accurate given that the first order was accurate? Well, you're just going to take the number of accurate orders that are left. We used to have 987, now we're going to have 986, and you divide by the total number of orders remaining. There were 1,118 orders, now there are 1,117 orders. Notice that the number of accurate orders goes down by 1 because we already pulled an accurate order out of the hat, and the number of orders, goes down by 1. Because we pulled an order out and we didn't put it back in. That's what it means to select without replacement. So it's a little different. It's very similar. It's close to what we would get using the selection with replacement, but it's just a little different. Then you multiply those together and you get 0.779289 approximately. So here are our probabilities. The probability of selecting 2 accurate orders from our sample when we're selecting with replacement is 0.779383. So if we put that second order, or if we put that order back in and then we choose again, the probability is about 77.9383%. That's the probability of getting 2 accurate orders. Now, if we do exactly the same thing, but this time, rather than putting the order back in after we've selected the first one, we leave it out and then we select a second one. This is selecting without replacement. And we get a slightly different probability of 0.779289. This one ends in 383. This one ends in 289. There's not much of a difference between these two. Now let's talk about the independence of events. This is related to what we're talking about as well. I know it seems like it's an aside, but it's related as well. Now this is a term, a definition. We say that 2 events A and B are independent if the occurrence of one does not affect the probability of the other occurring. So if A happens, it has absolutely no effect on the probability that B happens. We say that several events are independent if the occurrence of any of them does not affect the probability of the occurrence of any of the others. And of course, this is almost obvious. I almost didn't put it on the slide. If A and B are not independent, they are said to be dependent events. So let's think about these ideas. It says, let's revisit that example. It says, let event A be the probability of selecting an accurate first order. And let event B be the probability of selecting an accurate second order. When the orders are selected with replacement, so you've got your orders in a hat, you take it out, take one order out, and then you put it back in, and then you select again. Are the events independent or dependent? Well, I would say since you're putting it back in, since you're selecting with replacement, the probability of selecting a second accurate order is not at all affected by what happened with the first order because you put it back in. The pool that you're looking at is exactly the same as the pool that you were looking at when you selected for event A. So these events are independent. Selecting that first order does not at all affect the probability of selecting the second order, so we say the events are independent. The total number of accurate orders and the total number of inaccurate orders, or accurate orders and the total number of orders, not just inaccurate orders, but the total number of orders in our sample, it remains, or those two numbers remain exactly the same. And so the probability of selecting the second accurate order is not at all affected by selecting that first accurate order. And remember what we did, the probability of selecting the first order that was accurate was this, and then the probability that the second order was accurate is exactly the same as the probability that the first order was accurate. They have no effect on each other. So the events are independent. So they're, in this case, the same, and you just multiply. Now think about this. When the orders are selected without replacement, are the events independent or dependent? Well, if I took an order out, that actually changes a lot of things. In event A, if I selected an order, and then I didn't put it back, now I've changed the total number of orders in my hat, if I'm thinking of all of these guys in a hat, and I've also changed the total number of accurate orders. So that's changing the probability for B. So that means these events are dependent on each other if we're selecting without replacement. Selecting that first order does affect the probability of selecting the second order. So we say that the events are dependent. And in this case, both the number of orders and the number of accurate orders decreases by 1. And so we get this. We're getting a very similar decimal here. But the fractions, that second probability is just a little different than that first probability. And it's because we selected without replacement. So we want to keep this in mind. When you're sampling with replacement, that means you put it back in. Those selections are going to be independent events. because the set that you're selecting from is exactly the same as the set you were selecting from before. Because you put everything back in. That's what with replacement means. So if you're sampling with replacement, the selections are independent events. If you're sampling without replacement, taking some out of the sample changes the remaining like sample space, basically. It changes what's left. So in that case, the selections are dependent events. Now, some students might say, are there any shortcuts for this? Is there any time when I can just assume that the events are independent when they're actually dependent? Do I really have to think through this every time? And I honestly would say I would prefer that you would think through it every time, because it's really important to know the difference between independent and dependent events, and to understand how those labels, those designations affect probability. But we've got a guideline in our book. It's called the 5% guideline for cumbersome calculations, according to Mario Triola. And this is just giving you a guideline when Mr. Triola says it's okay to treat the dependent events as if they're independent. And here are the criteria. We are going to say that when we're sampling without replacement, so you take some elements out, and then you're not putting them back in, and then you're just taking another one, and then you're taking another one, and you're not putting them back in. So you're doing that. That's sampling without replacement. And when the sample size n is no more than, that's less than or equal to, 5% of the size of the population that this data is supposed to represent. In that case, we can treat the selections as being independent, even though they're actually dependent. We're sampling without replacement, so that means they're dependent. But if the sample size is less than or equal to 5% of the size of the population, you can treat them as independent. That's what Mario Triola is saying here. So let's revisit this example from before. It says, use the data in the following table, which lists our drive-through order accuracy at 4 fast food chains. Assume that the orders are randomly selected from those in the table. And then the question says, if 2 orders are selected, find the probability that both orders are accurate. Assume the selections are made without replacement. And here's a question. It says, when would it be acceptable to assume that the selections are independent, even though they're not? When? When would it be acceptable? Well, we've got to go back to that 5% rule. In order to get started, I need to know the sample size. So we're going to fill in that table again. We're going to find the number of accurate orders by adding up all the entries in this row. We're going to find the number of inaccurate orders by adding up all the entries in this row. And then we total this column, and that gives us the total number of orders. So we do that first, just so that we have that lowercase n. That's our sample size. That's 1,118. Now we're going to think about that 5% rule. What did that 5% rule say? It said, if that sample size is less than or equal to 5% of the true population, then it's okay to treat the events as if they're independent, even though they're dependent. So we're going to assume that n equals 1,118 is less than or equal to 5% of that population, capital N. And then we're going to find the population size, capital N. So you've got this inequality. You're trying to get n by itself, so you divide by the 0.05. That's 5% in decimal form. And then you simplify that fraction over that decimal, or that fraction, which is that number over that decimal, and you get 22,360. That has to be less than or equal to n. Or alternatively, you could say that n has to be greater than or equal to 22,360. So let's interpret this result. What does this mean? What this means is, if the population of fast food orders that we're interested in is greater than or equal to 22,360, then the 5% guideline applies, and we can treat the events as independent even though they're dependent. Say, well, I guess the population of fast food orders is definitely greater than 2,000 or 22,360. There are a lot more fast food orders than that in the world. That's my understanding of this 5% rule anyway. So I think that 5% guideline applies, and we can treat the events as though they're independent, even though they're dependent. Now, I always like to compare. Here's the probability of selecting 2 accurate orders with replacement, and here's the probability of selecting 2 accurate orders without replacement. So those probabilities are pretty similar. The first 3 digits after that decimal point are exactly the same. And then the difference between this one and this one, that's a 3 and that's a 2. If we subtract, it turns out that they differ by 0.000094. So that probability of selecting 2 accurate orders with replacement and without replacement, the difference between them is this tiny little decimal, which is less than 1 in 10,000. And I put that exclamation point in parentheses because it's not a factorial. It's just meant that it's for emphasis. So since that difference is so small, I might say, well, since the difference is small, pretending that we're not doing this, pretending that we're not doing this without replacement. Sorry, I'm having trouble with my words for a second. Pretending that we're leaving them all in there. We're always putting it back, even though we're not, is okay, because those probabilities are so similar. Now, I don't know how that relates to that 5% guideline, but it makes me think that since these probabilities are so close, then maybe it wasn't a bad idea to use the probability of selecting 2 accurate orders with replacement, this probability, as an estimate for the probability of selecting 2 accurate orders from the sample without replacement. Okay, so we're going to summarize this learning outcome. There's a lot in this video. This learning outcome involved studying a few things. First, the multiplication rule. It says that if you're finding the probability that A happens and B happens, so whenever you see that word and, I want you to think multiplication rule. You take the probability that A happens and you multiply by the probability that B happens, given that A has already happened. And sometimes you got to think through that. And sometimes you have to adjust that probability that B happens given A happens. And that's especially important to adjust that probability when you're talking about sampling without replacement. Because if you don't put that order or that piece of data back into your sample, it changes. It changes the sample size. It changes some other values in your table, your summary table as well. So that's the multiplication rule. We also talked about the independence of events. We talked about the relationship between replacement and the independence of events, and then we talked about this 5% guideline. So let's quickly go over those and then we'll end the video. So here's the multiplication rule. Again, remember this is about finding the probability that A and B occur at the same time. So this is the probability that A occurs and B occurs. So it's the probability of getting that first accurate order and the second accurate order for our example, in our example. And we can use the intuitive approach. It says to find that probability that A occurs and then B occurs. You find the probability that A occurs and you multiply by the probability that B occurs, assuming that A has already occurred. So you might have to adjust that second probability. And we would represent that in symbols with this symbol here at the bottom right-hand corner of the slide. Now, the definition of independence of events is really important. We say that 2 events, A and B, are independent if the occurrence of one of them does not at all affect the probability of the other occurring. So if one happens and it has no effect on whether or not the other one happens and the probability that that happens, then we say the events are independent. And if they're not independent, we call them dependent. Now that's intimately related to this idea of sampling. Sampling is so important. It changes probabilities. So we want to keep that definition of independent and dependent in mind and think about how sampling affects independence. So we said that if you are sampling with replacement, so that means if you were to take some data value out of your data set and you put it back in, well, then the data set is exactly the same as when you started. So any probability that you calculate after that is going to be exactly the same as it would have been had you not have done anything at all. So these events will be independent. The selections are events that are independent because we're sampling with replacement. That means putting it back in. If we're sampling without replacement, so we take something out and we don't put it back in, but then we take something else out and we don't put it back in, and we take something else out and we don't put it back in. Every time we take something out, we change the sample. It's changing. So now any probabilities that are based on this new sample have been affected by the fact that we removed some data values. So these selections are dependent events in that case. And then lastly, we've got the 5% guideline. And this says when a couple of things are true, we can do the following. If we're sampling without replacement, so we're not putting things back into our sample, we're just taking things out and taking things out and taking things out. When we're doing that, and when the sample size n is no more than, that is the same as less than or equal to, 5% of the size of the population, capital N, then we can treat the selections as being independent, even though they're actually dependent. So that is it for our lesson over the multiplication rule. I'll see you in the next video to talk about the principle of redundancy.